Have you ever been stumped by a problem that just feels way too complicated? Well, today we're diving into something called D'Alembert's principle. It's this incredible hack from way back in the 18th century that lets engineers take the super messy math of things in motion and, believe it or not, turn it into a simple balancing act. It is a total game changer.
I mean, think about it. How do you get that perfect mix of thrill and safety on a roller coaster? Or how does a robot in a factory move with such incredible speed and precision? The secret sauce behind all of that is the ability to understand and control the wild forces of acceleration. And as you're about to see, it all comes down to one really clever idea.
Okay, so before we get to the brilliant solution, we have to really get a feel for the problem itself. And at its heart, the whole thing is about the huge difference between analyzing something that's just sitting still versus something that's actively speeding up or slowing down.
Right? Just picture it. Figuring out the forces on a bridge, that's one thing. They're mostly stable, constant. But trying to analyze a car hitting the gas or an airplane banking into a turn, suddenly the forces are all over the place, changing every single moment. That makes the math and just wrapping your head around it so much tougher. That's the world of dynamics.
So to even begin to tackle these kinds of problems, physicists and engineers have a go-to tool. And it all starts with maybe the most famous equation in the history of science, from the one and only Sir Isaac Newton. This right here is the absolute bedrock of mechanics. F equals ma. It tells us that the total force in an object is just its mass times its acceleration. This is the golden rule for literally everything that moves, whether it's a baseball you just threw or an entire planet orbiting the sun. And check out the huge difference here. In dynamics, the world of motion, the sum of your forces equals ma, a value that could be constantly changing. But in statics, the world of things at rest, everything is perfectly balanced. The sum of forces is a nice, simple zero. Now, which of those equations would you rather solve? The one with a moving target or the one that equals zero? Yeah, statics is way simpler. And this is where the hero of our story, Jean-Laurent D'Alembert, comes in. He looked at this big divide between the hard problems and the easy ones and had this flash of absolute genius. He asked a question that was so simple, but it was revolutionary. What if we could just make a hard dynamics problem look like an easy statics problem?
So he didn't try to reinvent physics or throw out the rulebook.
No, he started with the exact same tool everyone was using, Newton's second law. The foundation was solid. He was just about to look at it from a completely different angle.
And boom, this is the trick. It looks so simple it's almost silly, right? He just moved the ma to the other side of the equation, but that one tiny move changed the entire game. All of a sudden, he's got an equation for a dynamic accelerating system that equals zero. He literally turned it into a statics problem on paper. Now, to make this idea work, he gave this new math term a special name, the inertial force. Okay, hold on. This is not a real force like gravity pushing you down or friction slowing you down. Think of it as a conceptual tool, a fictitious force that's like a placeholder for the object's own resistance to being accelerated. By pretending it's a real force, we can treat the whole system as if it's perfectly balanced. This quote right here perfectly captures the magic of the whole idea. You've taken this complex, moving system, and just for your calculations, you've basically hit the pause button and frozen it in a state of fictitious equilibrium. Now you can use all the simpler tools from statics to figure it out.
So the whole process is this beautiful four-step hack. You start with Newton's law, you do that little bit of algebra, you invent this inertial force, and just like that, you get to analyze the problem as if nothing is moving at all. It's just an incredibly clever and elegant workaround.
Okay, so why is this so useful? Let's look at a classic example, something you've probably felt yourself. Standing in an elevator, right as it starts to accelerate upwards. You feel heavier for a second, right? So this table breaks it down perfectly. The normal Newtonian way makes you think dynamically. You're balancing the real forces against that changing ma term. But with D'Alembert's principle, you just add in that fictitious inertial force pointing down and treat the whole thing like a simple balancing problem where everything just has to add up to zero. You get the exact same answer, but the way you think about it, the mental model, is so much simpler.
And listen, this isn't just some neat trick for solving homework problems. It has become an absolutely foundational concept in pretty much every field of engineering that has to deal with things that move.
When engineers are designing the suspension in your car, they need to know how it'll handle bumps while you're accelerating. When they program a robot, they have to account for the massive inertial forces of its arms swinging around. D'Alembert's principle gives them a straightforward way to calculate all of these dynamic forces.
And you can see just how fundamental this idea is. For mechanical and aerospace engineers, it is part of their daily language. But even for a civil engineer, figuring out how a skyscraper will react in an earthquake, well, treating those seismic jolts as inertial forces is a direct application of D'Alembert's genius.
And really, that's the heart of it all. D'Alembert didn't discover some new hidden law of nature. He just gave us a new perspective, a new framework for thinking that turned complexity into beautiful simplicity. He showed us that sometimes the best solution isn't a new formula. It's just a new point of view.
It's a powerful idea that goes way beyond physics, don't you think? What happens when you reframe a challenge you're facing? When you just move one little piece of your own mental equation, you might just find that what seemed like an impossible problem suddenly becomes a simple one, just waiting for you to balance it out. Thanks for joining me.